Hi, we're going to get a little weird with this one. So we spoke about amphoteric substances, right? So we've got oh geez, I'm in the wrong, oh, whoa, 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 I tapped too soon. We're going to go back to at, I just want an eraser. Whoa, flying off the rails already. Amphoteric substances, I mentioned that in my previous slide, so I might not need to go into this too much. But substances that have the potential to act as either an acid or a base as the situation dictates. Which is interesting because the easiest way to spot an amphoteric substance is whatever is needed for it to act as an acid or a base. And in terms of water, the water substance acts as an acid when it donates an H+. So that means you have a bond to a hydrogen that can become a lone pair. And when it acts as a base, it accepts an H+, which means you have a lone pair that can become a bonded pair. So amphoteric substances, and this is not a hard rule, but a quick way to spot one is H atoms and lone pairs. And this is kind of weird because if you think about this for a while, what this tells you is being an acid has a little bit more to do with the electrons than it does to do with the H's. Yeah, specifically the hydrogen, when it's bonded to certain atoms, invokes an electronegativity difference so large that that bond is so lopsided that it could maybe end up transferring the electrons from bonded pair to lone pair. But really, it's more important that the electrons do that than it is that the hydrogen is there, which means there's another way to look at acids and bases. Aluminum chloride solutions are acidic. This is a substance where there's no H pluses, there's no OH minuses, and yet it is still an acid. What? How? Why? What? Yeah. So let me see, let me remind myself. Yeah, okay. So we're just going to cover everything here. There is another definition of acids and bases. It's named after Lewis, same guy who did the Lewis structures, and I think that might help if we kind of draw some Lewis structures, which, I mean, the Cl minus, we probably are not going to use. Oh, geez, nope. But we've got a lot of electrons. For the aluminum ion, we've got a lot of spaces. We're going to call our definition for a Lewis acid an electron pair acceptor. And a Lewis base is an electron pair donor. I kind of remember this because it's the opposite of what H pluses do, but it's also talking about a negative, which is the opposite of a positive. So a Bronsted-Lowry acid donates protons, a Lewis acid accepts electrons, right? You gain a negative versus give a positive. Kind of makes sense to me. So I want to clean this up a little bit because I need a little bit more room. But the classic examples of Lewis acids and bases are boron compounds and nitrogen compounds. So BF3 and NH3. And what ends up happening is nitrogen has a lone pair, and boron, being a group 13 element, only has 3 valence electrons as a neutral atom, which means there's an empty orbital that can pick up a pair of electrons. And so what ends up happening is In this case, we get a formal positive on our nitrogen and a formal negative on our boron. And you get these things called complexes. These complexes are where the electrons of one atom, both, are being donated into an empty orbital to create this covalent bond. But we've seen this before somewhere. When we talked about equilibrium shifting to begin with, one of the things I did is I took time to talk about coordination complexes and what are they called? No, yeah, coordination complexes. We said that copper can exist surrounded by waters, or copper can exist surrounded by chlorides. Well, the way that works is that these metal ions have lost electrons and therefore have empty orbitals. A lot of these are in the D shell. But what ends up happening is if we were to try and draw this, it's kind of covalent in nature. We've got this tetrahedral substance. Oh my God, my wedges are off today. Erase, create, pen. Much better wedge. But this chloride complex is actually showing that one of the lone pairs of the chloride has actually donated into one of the orbitals of the copper. If you count up the electrons, it all pans out. But what happened is shared electrons, I'm saying it backwards. Lone electrons become shared electrons. So in this case, the Cl- acts as a base because it had 4 lone pairs, and now it's showing 3 lone pairs and 1 bonded pair. So it donated electrons into a shared pair from a lone pair. It's this weird way of thinking about it where it's like not a loss of electrons, it's like a partial loss of electrons. You go from owning something completely to sharing it. That can be viewed as a loss. And then the copper acts as an acid. Because that had the empty orbitals, so it went from not having to sharing a little bit. And the same thing happens over here with the boron and the nitrogen. And boron chemistry is fantastically interesting because of this. You have this empty orbital that can accept electrons. Accepting the electrons in the case of boron causes a negative formal charge, which is not desirable energetically. So you can kind of play this game of like, oh, it has a bond, oh, it doesn't have a bond. Now, none of this actually explains why aluminum chloride is acidic. And it has to do with aluminum. When aluminum dissolves in water, it doesn't just stay aluminum in much the same way that copper doesn't stay copper. I believe that aluminum gets surrounded by 6 waters. But what happens is when you surround that aluminum with 6 waters, you get this crowded complex where all of the oxygens are donating some electrons into the aluminum. And what ends up happening is that one of these will actually try and seek to balance things out. In each of these waters, if you make a covalent bond with one of the lone pairs of oxygen, each of these oxygens has a formal positive. Right? I'm going to zoom in a little bit to show that a little bit clearer. What we have here is a substance where, the rest of the molecule's down here. But this is a formal positive, which is not great. And to help alleviate that a little bit, there will be an equilibrium where the aluminum complex will drop an H plus. And so in this fashion, we'll actually see this pair of electrons become a lone pair, and the H plus will yeet again. I'm going to keep using it until it gets not cool, which probably already isn't. And that will cause the H plus concentration to increase slightly. And it turns out that a lot of metal ions will actually perform this, and you'll see that certain metal ions will create an acidic solution. Now the chloride, you might assume, has the potential to pick up some of those H pluses and keep it neutral, which is something we're going to get to in another lesson. But it doesn't, because HCl, like if it's stuck together, doesn't stick together. We've covered that. It dissolves into H plus and Cl minus. There is a hierarchy of these theories. If a substance is an Arrhenius acid, then it is a Bronsted-Lowry acid. Right? When hydrogen chloride dissolves in water, hydronium is the only positive ion in solution, the Arrhenius definition, and the HCl donated an H plus to H3O plus. So it is acting as a Bronsted-Lowry acid. If a substance is a Bronsted-Lowry acid, it is a Lewis acid. Well, the water here acts as an acid, and as we saw in the previous slide, when you have an H2O becoming an OH, the way that happens is that these electrons become a lone pair. So from the perspective of this OH bond, the O accepts electrons from the sharing between the O and the H. So that's your Lewis acid framework for saying, yes, the H here is acting as an hang on. Yes. The H here is acting as an acid. The hydrogen's acting as an acid because it is... No. The oxygen's acting as an acid because it accepts the electrons. So the water here, it acts as an acid. It's a little bit harder to make this connection, but that bond is where you see the Lewis acid behavior. Yeah. That makes sense because what you make is the base, right? Right. The converse is not always true. So we've seen examples where you can see reactions for the Bronsted-Lowry acid where we're able to label this as an acid because of donation of H+, but there's obviously no hydronium present. And then we saw in the previous slide there are several situations where a Lewis acid is a Lewis acid, but then there's no protons moving around to show that there's a Bronsted-Lowry. And I drew this picture to really kind of sum things up. The smallest categorization of acids is the Arrhenius. All Arrhenius acids are Bronsted-Lowry acids, but then there are some Bronsted-Lowry acids that don't fall into the Arrhenius bin. And then all of these would be considered in a Lewis framework acids, but then there are plenty of substances that act as acids that don't fall into those two and are considered Lewis acids. Thanks for watching.